Okay, so this is figure 283.1. This is the second video on Bayesian games today. Um, this is an example of when information can hurt. So if it's just a one-player game where one player is making the decision, more information is better, because the worst thing you could do is just ignore the information, but otherwise you could benefit from the information. But in two-player games, more information can sometimes hurt. Okay, let's see what we mean here. The black box here on the outside tells you what player 1 knows, and player 1 doesn't know which of these two games is being played, which is why it's contained within the same box. Player 2 also doesn't know which of these two games is being played, and both of them believe that the game on the left is being played half the time, the game on the right is being played half the time. The game on the left is called state omega 1, so if you're in the state of the world omega 1, you're playing this game. If you're in the state of the world omega 2, then you're in this game. Okay. Consider these players' best responses. So just consider player 2 for instance. What would be player 2's best response to T? Okay, if player 2 plays L, then player 2 gets 2 times epsilon. With player 2, and that's true in either state of the world, so 1/2 of 2 times epsilon plus 1/2 of 2 times epsilon is 2 times epsilon. If player 2 plays M, player 2 gets 0 half the time and 3 epsilon half the time. So that's an average, basically. So that means in expectation, player 2 gets 1.5 epsilons, right? 0 times half plus 3 epsilon times half is 1.5 times epsilon. If player 2 plays right, player 2 gets 3 epsilon half the time, 0 half the time, and so again that is also 1.5 times epsilon. So if player 1 plays T, then player 2's best response would be to play L, right? If player 1 plays B, we can apply the exact same logic. And again, player 2's best response would be to play L. And so for this game, the only Nash equilibrium will be B and L. So, because L becomes player 2's dominant action, and given that player 2 is always going to play L, player 1 will always choose B in either one of these games. So the Nash equilibrium will just be BL, and that is the only Nash equilibrium. On the other hand, now consider a different game. So in BL, both players end up with 2. But if player 2 had more information, we wouldn't end up with BL. For instance, if player 2, now consider a different game, where player 2 knows which one of these two states is being played. If player 2 knows which one of these two states is being played, then player 1 knows that player 2 of type 1 will always play R, and player 2 type 2 will always play M, right? Because 3 epsilon is greater than 0 or 2 epsilon, and 3 is greater than 0 or 2. Oh, here the assumption was that epsilon is a positive number between 0 and 1/2, just to be clear. Right, so because player 2 will always play, of type 1 will always play R, and player 2 of type 2 will always play M, player 1 will always end up playing T, right? Because that way it's just a choice between 0 and 1 or 0 and 1. So then, with more information, the Nash equilibrium, instead of BL, becomes T, comma, R, M. And in T, R, M, player 1 gets 1 instead of 2 earlier, and player 2 gets 3 epsilon instead of 2. And 3 epsilon here would be some number between 0 and 3 by 2, which again would be less than 2. So there you have it. You give player 2 more information, and that can actually hurt in this game. Okay, so meet you in the next video.